an example of a string which has a non-uniform density, and I'll show you how to derive its velocity function, and then we can calculate how many seconds it will take a wave to travel across the string. Let's say you have a string that is a length of 10 meters, and there's a tension of 20 newtons on it, again, right? But its density is non-uniform. At the left end, the density is equal to, let's say mu is equal to 1 kilogram per meter, right? I'm just making it an easy number. And then at the right end, the density is equal to 4 kilogram per meter, right? And let's say the density is increasing linearly. We could write something like this: u as a function of x is equal to mx plus b, right? And we can put what the y-intercept is, what the slope is. So what would the y-intercept be? Well, at the left end, when x equals 0, right, the string's linear mass density is 1. So that would be u of 0, that would be 1. So that's basically the y-intercept, right? We can have any kind of function here, linear, quadratic, cubic, or any function, and we should still be able to carry out this step. The next thing is we need to find the slope of the function. So we know that the string is 10 meters long, so u of 10, so we just put here 10m plus 1, right? And that's equal to 4. And then m is equal to what? 3 over 10, which is 0.3. Okay, so the u of x function is going to equal 0.3x plus 1. Let's see if that works. When I put 0 here, I should get 1. And when I put here 10, I should get 3 plus 1, which is 4. Right? So what is its velocity going to be, and how long is a wave going to take to travel across that spring? Like this. And we had 2t sine theta is equal to dm v squared over r. And then we're going to say, make the small angle approximation, 2t theta. And then dm is equal to mu dx v squared over r. The only difference is now mu is this function, right? 0.3x plus 1. Then we're going to say the dx, which is the length of this from here to here. This is r, and then this is 2 theta, right? So it's going to be the same kind of derivation that I had in the theory video. Then the dx is going to be r times 2 theta. So 2t theta. This is the small angle approximation. And then you have here dx is r2 theta. And then the r cancel. And the theta cancel. And then the 2 and the 2 cancel. Well, it actually comes out to be, you don't have to always do this, but I'm just showing you that the equation comes out to be the same. V is equal to v squared over mu. Well, what you see from here is that the velocity equation didn't change. All that changed is that the mu is now non-uniform, so the velocity of waves along the string are non-uniform, right? So now we can apply this to our string. So you don't have to do this derivation every time from now on. You already know that this equation works, but then you put the mu function. So then you have here v is equal to, the tension is uniform, so square root of 20 over square root of 0.3x plus 1, right? And what is that equal to? Well, this just gives you a general function, v as a function of x, right? We want to know how long a wave takes to travel the length of the meter, 10 meters, right? So this is equal to dx dt, right? And now we can make this an integral problem. Square root of 20t is equal to square root 0.3x plus 1 dx. Then I can integrate 0 to t, 0 to 10, right? I can take the integral of this, and we can do that on the TI calculator. And then this one is just going to be square root of 20t. Variable x, then I'm going to go 0 to 10. Okay, this one gives me 15.555 repeating 5s. And the time is going to be that divided by 20 to the power 0.5. It's going to give me 3.478 seconds. Okay, let's see if that makes sense. if the density of the wave hadn't changed, what would have happened? Its linear mass density would have stayed 1 kilogram per meter, let's say, right? The velocity of the wave would have been what? Square root of t over mu, and that would have been square root of 20 over 1, which is just square root of 20, right? So that would be 20, and then that would be meters per second, right? Now how long would it take a wave to travel across the length? So it would be velocity equals distance over time. Time would be distance over velocity. So it's a 10-meter wave over 4.472. So 10 divided by 4.472. Then that would take 2.236 seconds. So it's taking it quicker, huh? So if the rope is getting thicker, or getting denser, right? The velocity is going to get slower as it progresses, so it's going to take longer time. If the density stays the same, 1 kilogram per meter, right? The velocity stays the same, it should take shorter time. So 3.47 seconds, slightly larger than 2.236 seconds, so that actually makes sense, okay? So we can have any function of distance for the linear mass density, and we can use this technique to calculate how fast waves propagate along that string and how long it takes a wave to propagate the total distance of the string, okay? Thank you very much.